Hello, everyone. Welcome to this live stream. I hope you can hear me. I'll just wait for maybe 1 minute or so just to make sure that we've got more people joining. Um, Again, the objective of this session is to basically go through papers that showed up on our social feed that we think you should find interesting to read, because as you know nowadays, there's so much happening in the thing, whether on LinkedIn or other social networks, where there's so much content. Most of the content are obviously not good quality. So a lot of the good quality stuff get buried in this nonsense that we are now having, especially with AI generated stuff, where people are looking for clicks and all this sort of stuff. So yeah, today I was actually going to share two papers, possibly three, but unfortunately I have to do only one paper because I'm going to travel, unscheduled travel today, so I can be somewhere early morning tomorrow. Next week we will continue with the other papers that I wanted to share today. So let me get started. Let me share. So this is the paper that I would like to share with you. It's a very interesting paper. So discovering symmetry groups with flow matching. As many of you know, symmetry is very useful, not just in physics, although traditionally, physicists were one of the first clients of this idea of groups, symmetries and groups. But nowadays in machine learning, these ideas are pretty much, becoming mainstream. In the case of machine learning, practitioners who want to deploy symmetry into their training, the type of practitioners who do something called geometric deep learning, they usually have to specify the relevant symmetry before the training their model. So basically, the essence of this paper is uh, whether symmetry can be inferred from data. So instead of figuring out the symmetry before you start training, you look at the data and then that tells you which symmetry you should use for your training. So the proposed method is called LieFlow. It treats this discovery of symmetry as a learning task, um, or in a more precise way, as the task of learning a distribution over Lie groups. So again, I will just say, to read this paper, you need to understand group theory, in particular Lie groups, which most of you guys, who have enrolled at QF Academy, and the ones that are on our private audience mode here, I know about Lie groups because I've been following your progress. So you really need to understand Lie groups. For you who already know Lie groups, these papers like this will give you some sort of motivation to think to why they are interesting. For those who don't know anything about Lie groups, maybe this could stuff like this can give you a motivation to why you should learn about them. So why is it interesting and important to know about the symmetry? This is basically because knowing the symmetry can help you change how we can build a model to make it more efficient. For example, if a task doesn't depend on, say, orientation of an object, then the model doesn't need to rediscover that from thousands of possible rotations. I'll give you a simple example using our adopted cat house here. This is a cat, okay? So if I rotate this, well, still the same cat. If I rotate it again, well, it's still the same cat. And if I continuously do this, it will still be the same cat. This might sound like very trivial for us, but for traditional neural networks, deep neural nets, trained on, say, imaging and these things, they struggle with this, okay? they would need like thousands of samples of rotated examples of this cat in order to be able to identify that this is a cat. Okay, so suitable symmetry assumption can reduce the amount of data needed and avoid learning the same pattern repeatedly in different coordinates, right? So therefore, this makes the whole training process much more efficient. So you have a better, much more linear architecture and more efficient training. So, but it comes with a catch. If you don't know which symmetry you are starting with, this can be a problem. If we force a model to respect specific symmetry transformation that the data doesn't actually support, well, then it's as useless as not using it. Okay, so the goal is really to not to put more symmetry necessarily into the model, but to identify what sort of symmetry that are naturally present in the data in order to do this. So this is one of the reasons why I thought this is very interesting, for especially for those of you taking our Lee groups with application programs. So the way it works, um, you pick, so inside the larger family of possible transformation, so you pick, you start with a big, large group. They call this on the paper the hypothesis group. Inside this large family of possible transformation is your smaller set of transformations that truly leave the state unchanged. So leaves your thing, your stuff, the stuff that you want, your data, unchanged, invariance, under the transformation. So the goal is really basically to identify which transformations in this hypothesis space preserve the underlying data, so that if we apply one of these transformations, the data should still look statistically like it came from the same source. Okay, so there shouldn't be any difference by applying the transformation. That's where the invariance term comes in. Um, the key difference between this framework, from what I can understand, disclaimer, I actually haven't read the full paper in depth. So, I picked it this morning over coffee. I was just going over the essence, so to give you a flavor from what's inside, so you can hopefully be curious and explore it. I will myself go and dig deeper into it, and possibly make this paper as a possible capstone project, for some of our students taking the Lee groups with the application program, for instance, or my own live bootcamp group theory 360, so that they can do some work around this. So what's the difference between this? Because there are other frameworks, geometry toolkits, for integrating symmetry into your model. One of the key differences is in the earlier approaches, often you try to learn the generators directly. Okay, so the term generators, again, this is technical. You need to know group theory. I'm sorry, I won't give you group theory 101 here on the thing, but for those of you, especially on the thing, on the audience mode, coming from QF Academy, you know this. So this framework takes a different route. Basically, instead of asking what the generators of the symmetry groups are, it learns the probability distribution over the larger hypothesis group. So the learning distribution should, basically place mass on the transformation that preserve the data, and little to no mass elsewhere. So for a continuous symmetry, the probability mass spreads along, say, a continuous family of transformations. For finite symmetry, it appears as collection of, say, peaks. So basically, this is one of the key differences between this in a nutshell. Okay, this is just a very compact pitch to why this paper is interesting, what makes it different from the other things that we have seen before. So just I know I said I wouldn't give a Lee theory 101 stuff, but I'm tempted now just to think. So Lee groups gives us both the algebraic and geometric discovery of transformations, basically, in one paragraph. The group tells us how transformations are composed. The Lie algebra describes basically the infinitesimal directions near the identity, and the exponential map links the two. So starting with a small direction in a Lie algebra, the exponential map can produce a finite transformation in the group. For a matrix group, this is the matrix exponential and so on. It is basically the mechanism that lets the method make updates which still stay inside the transformation group instead of moving arbitrarily through the ambience, the entire ambience data space. So it's really a very interesting paper. I recommend you to go and read about it, and give your feedback. In particular, if you are enrolled in QF Academy with us, this could be something like this could be part of your capstone project. So a takeaway is that symmetry is not something that we necessarily need to impose on a model. It can be treated as something to be discovered. Okay, and this is the point of this framework. By searching over by searching for a distribution over a large family of transformations and identifying where the distribution concentrates, and that tells us something about the thing, the core uh, uh, idea. The other thing is I found is the paper still somewhat limited by the choice of a hypothesis group. Maybe because of obviously you write a paper, you have only maybe I don't know a few weeks or a few months and these things, and I think there's still some. Well, this is also an opportunity, by the way, especially for those of you enrolled at QF Academy, because maybe you can expand the hypothesis group in order to create more empirical results, that you can share with the community or with your whatever, integrate into your work. So yeah, so that's basically the thing. And again, I'm going to repeat why this caught my attention is because it aligns with us, with the quantum formalism community, right? Because it integrates group theory, which is something that we have been talking about a lot, not just on our community post, but also within our own curriculum for QF Academy. In fact, all the mathematics that you need to understand papers like this is available right now at QF Academy. So go to quantumformalism.academy if you want to have um, a deeper understanding of group theory, and in particular Lie groups, Lie algebras and representations. We have something for you. And in fact, we have a prerequisite as well. If you don't know anything about groups or topology or manifolds, we have a program on a crash course on groups, topology, and manifolds that you can use before you jump to go and learn about Lie groups. That's because Lie groups are not just groups in the algebraic sense; they are also smooth manifolds, and as such, there is also an underlying topological structure that one cannot ignore. So you need to know this, and then the interplay, the interaction between the algebraic and the geometry and the topology. This is something that you then go and learn within the program of Lie groups. Okay, so that's all I have to share. I promise some of our audience members on the private mode, our Substack founding members and some select QF Academy members, that I've sent a private link, so you can and it comes with a private chat. You can send me a message. I will take some questions, and then maybe I will look at also on the public channel, LinkedIn and YouTube, to see if I have any other questions. If you are on the public channels, LinkedIn or YouTube, please feel free to basically ask a question. I will stop sharing, And let me go and check the chat here to see from our founding members on the private, on the audience mode that we have. So I have a question here. What is the difference between the hypothesis group and the symmetry group being discovered? That's a very good question. Well, basically, the hypothesis group is the family of um, transformations that you choose before the training. So this is your starting point. It basically defines the search space to which you will find the actual symmetry group for your data. For example, you can start with all the rotations in 3 dimensions, for instance, even if the data only supports a finite collection of them. But then you have the entire space of all rotations. Then it gives you the wiggle room, to go and look for the symmetry group within this whole transformations that preserve the data distribution. So the LieFlow basically learns this distribution over the large hypothesis group, and it uses the high density regions to identify, to give it a clue to the transformation supported by the data. Okay, so this is all about your data. So it makes life easier as well. You might as well start with something big and then narrow your thing. Let your the learning does the job for you, to go and find the optimal symmetry group for your stuff. Basically, the method does not infer symmetries from the unrestricted universe of possibility. It basically just searches within a group selected by a researcher. So this is like some. Let's suppose the thing is actually it's your hyper. It's a hyper parameter you choose as a starting point, I guess, in a loosely way, and then the rest is fine tuned to find your thing, the correct symmetry group. Okay, let's see. Do we have anyone else on the public channel with questions? And then I will go back again to the community. Let's see. I need to find where the chat. This is a new platform, so yeah. I'm still figuring out. Yeah. Anyone on YouTube or LinkedIn? Have you got any questions for me? If not, I will move because there are more questions on the thing for our founding community members on the thing on the audience mode. Okay, so let me go back again to see if I can take a few. I don't know how many more questions are there. I still have about 10 minutes, so hopefully I can fire. This one, John. Why does the method transform a data point first instead of comparing two naturally occurring counter examples? Well, I don't think I think the paper doesn't assume that the data sets contain pairing examples showing the same object before or after the transformation. Okay. What I understand just by scanning it, scanning through, again, I said I have to go more into the details of the paper, but from what I can understand, that is basically it creates a self-supervised training signal. It takes a data samples, applies a transformation sampled from the hypothesis, from the large hypothesis group, and it constructs a path that reverses that transformations through the group action. Okay, so that's basically, so then the model learns the infinitesimal transformations associated with the chosen path. I hope that answers your question. Let me turn back to YouTube or LinkedIn again on the thing. Do you have any questions? Okay, so I'll go again on the private chat. By the way, for privacy, I'm not pulling the thing for the thing to not show our members. Sorry, I called one of them by name before. Sorry for that. The private chat meant to be the audience mode where you are free to ask any questions, without being fear of, feeling like, hold back, or I'm asking a stupid question or something. So that's one of the reasons why we invite our founding members and QF Academy members to join that, so they can ask free. So the other question I have is is the model learning a path through the data space or a path through the transformation group? Um, well, this is somewhat connected to the previous thing, that the previous question, but the short answer is both appear in the construction, but the object predicted by the model belongs to the transformation side. Of course, the data points move along an orbit generated by the chosen group action, right? But of course, the network predicts an infinitesimal element of the Lie algebra associated with the hypothesis group. I hope this is at least this is what I understand from the thing. Looking at the going through the thing, the paper. Let me go back again to YouTube and LinkedIn, public chat. Any other questions? I think I have time for two more questions, and then we have to wrap up. Any questions, please? Don't feel shy. This is why I'm here, just to basically, be able to exchange, some paper that I found interesting. That I know the profile of our community members that you might also find interesting. So yeah, I hope you go and read it. Let me go back again to, okay, I'll take three more questions if there are, and then that's it, we wrap up. Okay, so this one says, how can a continuous flow represent a discrete symmetry group? Well, the flow itself, of course, is continuous, but the learning distribution can be sharply multimodal. So for a fourfold symmetry rotation, of course, the expected result is not a uniform distribution over all possible rotations, right? Yeah, it is a distribution with four concentrated regions, each corresponding to one validated rotation. So I hope this answers the question. Again, this is what I understand anyway, but maybe go through the paper and come back to me if this is not the case. I will also try to go over it, and then I'll get back to you to take back anything that I say that might not be the case. But from my understanding, strictly speaking, a finite at finite model capacity and finite numerical precision, the model can learn peaks near those group elements instead of doing it at isolated from an isolated mathematical point. So the support is basically to interpret the probability density, to look where the probability density concentrates, and that will give you the hunch to where your stuff is, what you are looking for. I suppose here, this is a bad analogy. I suppose this is similar to thing that people in quantum do, quantum physicists do, right? They look at probability distribution. The highest the thing. This is where most likely you will find your particle or something, right? So similar thing here. Okay, so that's one question. I have two more questions on the private audience mode for our founding members. But is there any other questions on the public chat for those on YouTube or LinkedIn? I don't want to just, do it just for our, of course, our founding members and QF Academy members who are on the audience mode private are very important to us. But we also want to make it as accessible as possible. That's one of the reasons why we are streaming this across the platforms, across YouTube and LinkedIn. Well, I give you 20 seconds while I take a sip of water before I go to the final two questions from our other audience, and then off I go. Okay, so let's see. Okay, does the framework recover the group in the full algebraic sense? From what I can see, not directly. Instead, what it does is it estimates which transformations are supported by the data distribution, and then from those samples, one might infer a family of finite or continuous symmetry groups, such as the fourfold rotational symmetry or rotational symmetry around an axis, for instance, and then you go from there. That's what I understand. So the method doesn't automatically return a minimal generating set, defining relationship or proof that a recovered transformation forms an exact subgroup under the composition. I think, unless I got something wrong. Okay. On YouTube, do you have any questions? I really like when people ask questions, so I'm not just blah blah blah. Okay, at least we had our founding members and QF Academy members asking questions. So thank you for that. But it would be nice to also have others from the public asking questions. No, I'll give you 20 seconds. You can go and think about it. Ask your questions. I'm here to answer them. Okay, well, if there are no questions, then we can leave it here. As I said, I was going to review two papers, but unfortunately, because of last-minute travel arrangements, I need to leave now or soon. But yeah, thank you so much for joining, and thank you for our founding members and key of academy members on the audience mode private chat for you know um, asking those interesting questions. I hope you found this paper interesting. For those who I see new people joining on the other platforms, um, for those who have just joined, this is the paper. Okay, I highly recommend it. You can go and read it. Let me know what you think about it. And as I said on the during the introduction, we will try to make this as this paper as a capstone for our community members taking our group theory Lee groups program, because this is a very interesting thing. It comes also with code, so you can go and play around with the code, which is a very always a very good thing, because a lot of these papers, with these things, very often they're just theoretical in nature. Not or if they run the experiment, they don't share the code, the source code, for you to go and try to reproduce or try to extend the framework. But this piece of work does that, which is one of the reasons that we highlighted it, because a, it's very interesting, b, it comes with code, so that you can go and play around with code, and the code is open source as well. So yeah, this is the spirit that we will be going forward, is to share papers that ideally have um, the experimental stuff available for free, accessible. In particular, the code that's been generated to support the research. That way, our community members, all of you, you can take that and run your own experiments and maybe come and formulate new ideas on top of that. So, and this is how, these tools then become mainstream, because a lot of these things are not mainstream at the moment. So the only way to make it mainstream is to make it more accessible and make the awareness to these tools far more than what we currently have, right? Beyond these very niche conferences on geometry and machine learning, many people don't know this stuff. This is one of the reasons that at QF Academy, we really want to emphasize this. Yeah, I hope you enjoyed it. And I'll see you next time. And wherever you are, and whichever team you are supporting in the World Cup, good luck to you. Obviously, I'm supporting England because I'm based in the UK. I'm actually conflicted because um, I support England, but I also support France, and I support Portugal as well because I have my roots in Portugal as well, and some and the African continent as well because I do have African roots as well. So yeah, and Brazil as well. So yeah, I have more. Let's say my path to being happy is much more wider than most of you who only support one team. I have more options. So yeah. So anyway, thank you so much for joining, and I'll see you next week. Bye for now.